ये वही तुम लोगों का कर्नल वैल्यू है, मतलब ब्लॉक साइज जैसे हमने 11 by 11 डिफाइन किया था, ये 5 by 5 है, तो इसको चेंज करके मतलब जितना ज्यादा तुम बड़ा लोगे इसको उतना ज्यादा ब्लर हो जाएगा, वैसे क्वेश्चन ब्लर। ओके,
ओके।
so this was edge detection. Okay, now contour detection. So contours is a bit different than edge. So basically when you, matlab contour is also a type of edge, you can say. So when that edge is continuous and maybe enclosing a particular region which is of same intensity or same color, then that will be defined as a contour. Okay. So this is a, you can say a particular kind of edge. So this is the function for contour detection. So so this function will give you two things, that is contours and hierarchy. I will tell you what hierarchy is. First, let's see what are the arguments in the function. So first is the image. Second is the mode. Wait, I'll tell you with the help of graph. Right. So हाँ, इसमें also I forgot to tell you one thing. इसमें also first you will do edge detection. After converting it into grayscale, after converting the image into grayscale, you will first do edge detection and then you will apply this contour detection wala function because it will be easier. Okay, so uh, right. So first is the image that you want to do contour detection on. So this is the image that we got from edge detection that we have used here. Okay, for contour detection. Then the second argument is, okay, it will tell you the contours that you want to detect. So you have different kinds of contours here. Like the outermost contour will be this between the background and the face of this animal. Then you can have contours inside a contour as well, like the contour of this eye, the contour of the nose. So these are two different kinds of contours, the external one and the internal one. So if you type here RTR list, then it will show you all the contours. If you type here just external, then it will only consider the external ones. So these are two kinds of contours. This is also, you can say that this is what hierarchy is. Okay, that you get a parent contour and then the more inner you go, it will be children contours. Okay, so that is what hierarchy is. So if you do not write hierarchy here, it will not consider uh, all like different as parent and children. It will consider it same. All contours will be same.
दीदी आपने एक्सटर्नल के लिए बताया, अगर अपन को इंटरनल वाला कॉन्टूर चाहिए हो तो उसके लिए क्या करते हैं?
तो इंटरनल यूज कर लेंगे, राइट? नहीं, इंटरनल नहीं, वेट, इसका डिफरेंट एट्रीब्यूट होता है कुछ, ट्री या कुछ, वेट, यहाँ पे इंटरनल के लिए आई एम नॉट श्योर, इंटरनल के लिए मेरे को देखना पड़ेगा, बट एक्सटर्नल के लिए एक्सटर्नल है। ओके, okay, and the last attribute is chain approximable. So this is basically how you perceive a contour. So if you have a continuous shape, like say for example, if you have a triangle, then in chain approximable, the contour will only be the 3 points of the triangle. And if you change it, if you change this attribute to some other attribute, then it will maybe consider, if you change it to chain approx none, I guess. Yeah, it is none. So then it will consider all the points, all the pixels along the contour. Okay. So that is what chain C approx simple and chain approx none will do. So this function will return the contours, and then if you want to view the contours, then you will use this cv dot draw contours function. So this will draw it on the image that you want to view it on. Okay, so let's see. First you converted it to grayscale. This is the contours that you get. Okay, so you can see define here the color of the contour. It is 255, that is, it is green in color. This one will be the thickness of the contour, and so on and so forth. Okay, -1. -1 will tell you that you have to print all the contours. If you write 1, 2, 3, then it will give you the particular contour that you want to print. Okay, so this is the function for contour detection. I will go on to the slide bit. Okay. See here we have just printed the contours and we have printed the contours on the image. Okay. So any other doubt? Okay, so that is
Didi,
all
what
from.
does it save
Uh-huh.
the counter? What does it save the contour as? It saves it
The
as a
pixels.
matrix. Yeah. Okay. And what's the
Yeah, yeah.
thickness? You can set the thickness as well.
Thickness you can, yes, thickness we can mention. See here. While we print the contour, we can mention the thickness. Okay. So this one is it tells you the thickness. Okay, so the
Didi,
image. Hmm.
in this code, we have used the image IM, which is the one which is not converted into grayscale.
Yeah, because we have printed the contours on the original image itself.
Okay.
Yes. For processing, you have used grayscale only. See, this function, this grayscale image is image R. Then you have used image R for first edge detection, and then this edge detection image you have used here in the contour detection part.
Okay.
Okay. And for printing the contours on the, you have used the original image IM only. Okay, so that's all from image processing part. Viraj, do you want to continue?
Yeah, I'll take it from here.
I'll stop sharing them.
Yeah, yeah. So, how was the overall edges and contours part, guys? Any doubts? If you still want to ask something, or shall we proceed to the introduction to neural networks part? How many of you can hear me? Just raise your hands once. Okay, okay. ओके, नाइस नाइस। थोड़ा इंटरेक्टिंग रखना, ठीक है। पूरा वन साइडेड तो यार तुम भी बोर हो जाओगे, मैं भी बोर हो जाऊंगा। और ये वाला तो थोड़ा मैथमेटिकल सेशन होगा। आई ट्राई टू कीप इट कंसाइज एज पॉसिबल, लेकिन न्यूरल नेटवर्क्स में थोड़ा मैथ्स इंट्रोडक्शन तो बनता है, उसके बिना तो क्या ही करोगे। तो एनीबडी हैज सम आइडिया न्यूरल नेटवर्क्स, मशीन लर्निंग कितने लोगों को पता है थोड़ा बहुत कि क्या होता है? अनम्यूट करके बता सकते हो। एनीबडी? नहीं पता, नहीं बोल दो अनम्यूट करके।
भैया पहले एक प्रोग्राम को डेटा पे ट्रेन करते हैं, फिर उसके बेस पे वो प्रेडिक्ट करता है जब बाद में डेटा प्रोवाइड होता है तो।
बिल्कुल सही, बिल्कुल सही। तो बेसिक से ही उठाएंगे, नो डाउट उसमें तो। रिग्रेशन पता है किसी को? लॉजिस्टिक्स एंड लीनियर।
भैया जिसमें शायद
एक
बेस्ट फिट लाइन चूज करते हैं एट्रीब्यूट्स के बीच में ना।
एक फंक्शन निकालता है जो
हाँ,
हमारे डेटा को बेस्ट फॉलो कर रहा है।
बिल्कुल बिल्कुल, एब्सोल्युटली राइट। वो ये लीनियर रिग्रेशन इज फिटिंग अ स्ट्रेट लाइन टू अ गिवन सेट ऑफ पॉइंट्स। लॉजिस्टिकल रिग्रेशन की मतलब तुम्हारा कर्व एग्जैक्टली स्ट्रेट नहीं होगा, कुछ और रिलेशन आएगा उसके बीच में। तो यूज डिफरेंट काइंड ऑफ functions, activations you can say, to basically predict what can be the produced graph, basically, so in simple words. And neural networks is nothing but the same thing, that we train our data over some sort of predefined data ki matlab, this is, suppose I want to train a model over to recognize if this is a cat or a dog, as easy as it can go. कैट और डॉग में मुझे डिफरेंस अगर पता करना है तो आई विल बी लाइक, बेसिक सिंटैक्स वुड बी, I'll be supplying some input images with predefined classification. This is a cat, this is a dog, and then I'll instruct my model to learn whatever it can from this. And as output, it will just predict some accuracy कि okay, model trained, मतलब वो फिर उसी प्री डिफाइंड डेटा पे थोड़ा सा डेटा सेट उठा करके फिर अपने प्रेडिक्शन से बताता है कि कैट है या डॉग है। उस पे फिर एक्यूरेसी प्रिंट करेगा, इतना एक्यूरेसी, एंड देन यू कैन सप्लाई न्यू रॉ डेटा, अनचेक्ड डेटा फॉर द सेम, है ना? So I'll just share my screen and we'll begin with the session ahead. Are you able to see my screen, guys?
यस भैया।
Okay, okay. So let's begin then. Introduction to neural networks. So obviously न्यूरल मतलब सुना ही है तुमने, बॉडी में कुछ होता है, न्यूरॉन्स वगैरह। उसके बेसिकली वही चीज है कि तुम यहाँ पर अगर डायग्राम में देखोगे, इनपुट सिग्नल प्रोवाइड हो रहा है, बीच में कुछ तो वो प्रोसेसिंग होगा, और फिर बाद में आउटपुट सिग्नल देगा कि व्हाट एक्शन यू हैव टू टेक अकॉर्डिंगली। तो द एनालॉजी fits the same for a neural network. It's derived from a neuron. So the first neuron was the McCulloch-Pitts neuron, MCP, the most basic one. Like you provide the different inputs. Suppose those are some factors on some problem you want to decide ahead, and on what intensity that particular factor affects the output for your given function. I'll repeat, on what intensity that particular factor affects the output of your given function is defined as weights. Okay. And when you apply some condition, that if I apply some condition that is a summation of sigma wi xi, that is w1 x1 plus w2 x2, that is nothing but weight multiplied by the input. So nothing but how much that input is affecting your function. And if I apply some condition that this must be greater than some particular threshold number, If that is true, your function should output me the value 1, that is true. Or if it fails the condition that the resultant value is less than the threshold value, it will be output giving me the output as 0. Okay, so that was the most basic neuron that was earlier connected. uh, this T function, I'll just annotate a bit. This one, so that is nothing but the threshold function, because like if it's greater than some particular quantity, it will give you the output as 1. If it's less than some threshold, it will give you the output as 0. This is basically yes no type questions. So that was basically the limitation for this model, because we couldn't apply it to all our available data. Like in the real world, we have many other data that are not necessarily binary in nature, that is yes no type. There is also a chance that there are some other non-linear functions available for us to predict. So evolving from the MCP neuron, we go on to the perceptron model. So a perceptron model, the same thing. X1 is the input, X2 is the input. So and W1, W2, Wm, the same thing. The intensity with which the input will be deciding the output. That is nothing but the weight. Here, this you can notice W naught. Just a minute. So this W naught is nothing but bias. Bias, you can understand that if for the like मैंने पिछले स्लाइड में जो बात की थी कि तुम एक थ्रेशोल्ड डिसाइड करोगे, इस थ्रेशोल्ड के अगर ऊपर तुम्हारा वेटेड सम आता है, दिस विल बी कॉलिंग एज द वेटेड सम. अगर द थ्रेशोल्ड इज greater than this weighted sum, you will be getting a 0, and if the weighted sum is greater than the threshold, you will be getting as 1. So to simplify that, we just add a W naught quantity, that is bias. कुछ नहीं, बायस को नेगेटिव रख दोगे और फिर ओवरऑल तुम्हारा वेटेड सम अगर तुम ग्रेटर देन 0 पुट कर दोगे मॉडल में, serves the same purpose, nothing else. And there is one more thing in the perceptron model that is new, that there is an activation function, and also we train our model on the basis of the errors obtained in that particular run. Okay. मुझे बताना guys if you feel I am going too fast or you're not understanding something. Okay. So the basic difference here is we have introduced an activation function. Now we'll be discussing about that in the later part of the presentation. लेकिन अभी बस इतना जान लो कि you don't need all sort of inputs while you compute the further outputs. So activation function is nothing but to simplify all those ranges. Like there are chances कि तुम्हें -50 से +50 के बीच में सारे inputs मिल रहे हो, और फिर अगर तुम्हें output decide करना है, that is a complicated task for the computer to process. तो अगर मैं उसमें activation function लगा देता हूँ, for example sigmoid. Sigmoid function is nothing but 1 upon 1 plus e to the power minus x. So that the function will always give me the output between 0 and 1. So we can transform any non-linear value into a binary classification. Not exactly binary classification, but we can get a defined range for the same thing, that I'll be getting the value as between 0 to 1. That would be nothing but you can call, it would be easier for us to deal in probability terms. So the perceptual learning algorithm, there are 4 significant steps for the same. So firstly, the weighted sum, we multiply all input values with the corresponding weighted values, and then add them to determine the weighted sum. So mathematically, this is represented as this sigma wi into xi, that is nothing but x1 w1 plus x2 w2. And as I had earlier discussed, we add another essential term called as the bias to the weighted sum. Bias is nothing but to improve the model performance. That is nothing but we can call, in other words, a kind of threshold for us. Like you don't actually depend on the given factors all the time. There can be variation for the same. So you basically add that bias term to take care of that variation. Okay, you can keep that in mind. And next, an activation function is applied to the weighted sum, producing a binary or a continuous valued output. The same thing, like we need to suppose define our outputs on a given constraint. Like the range is not obviously you won't be playing from minus infinity to infinity for all the times. Your model will take too much. It would output many times garbage values because too large of a negative number will affect your training ahead. So for that purpose, we apply an activation function. And as I said, for the perceptron module, there are two key differences from the MCP neuron. The first was the activation function, and the second thing was we train our model based on the error we get in each of our run. So we calculate the error, and obviously we'll be taking the modulus for the same, or we'll be taking the squared error, because there are chances कि मतलब एक पर्टिकुलर x1 के लिए तुम्हें एरर मिला था +2 और x3 के करस्पॉन्डिंग आया था -2. तुम अगर दोनों को बिना मॉड्यूलस लगा ऐड कर दोगे, वहां पे 0 आ गया, लेकिन वहां पे एरर तो था, है ना. So that's why we need to add the modulus for the same. And the last step is nothing but optimizing this error. This we have defined the error function as a loss function, and we need to optimize it. That सबसे मतलब प्राइमरी टास्क जो था कि मुझे प्रेडिक्ट करनी है चीजें गिवन फ्रॉम अ गिवन सेट ऑफ डेटा. मेरे पास कुछ सेट ऑफ डेटा गिवन है, उस पर मैं अपना मॉडल ट्रेन करूंगा, और फिर उससे मुझे नई चीजें प्रेडिक्ट करनी है. कि सपोज यू कैन एल्गो ट्रेडिंग सुना है तुम लोगों ने? एल्गो ट्रेडिंग तो सुना ही होगा. हेलो हेलो. हेलो गाइस, एम आई ऑडिबल?
यस भैया।
यस भैया।
ओके ओके, यस नो कर दिया करो यार. पता चला मैं इतना कुछ बोल रहा हूँ और मैं डिस्कनेक्ट हो गया था. ओके, तो एल्गो ट्रेडिंग जो है नथिंग बट लाइक द प्रेडिक्शन कि ये वाला पर्टिकुलर स्टॉक कब हाई जाएगा, कब लो जाएगा, व्हेन वुड इट बी अ बुल, व्हेन वुड इट बी अ बियर. तो वो जो प्रेडिक्शन है उसके लिए तो काफी एडवांस्ड ऑप्टिमाइजर्स लगते हैं आगे. अभी तो हम बस बेसिक से शुरू कर रहे हैं. So we optimize the error function, that is nothing but the loss function, कि हमें सबसे कम loss वाला जो मॉडल है वो हमें expected होगा, because obviously you don't want any wrong predictions going on frequently. Okay, there is मतलब बहुत rare chances होते हैं कि तुम्हारा मॉडल 100% accuracy पे चल जाएगा in real world, है ना. लेकिन above 95 90% also मतलब काफी हद तक चल जाता है कि okay it's accepted. And so one of the optimizers we would be looking here in this deck would be gradient descent algorithm, the easiest of them and the most basic one also. So we'll be moving on to it. थोड़ा मैट्रिक्स फॉर्म में लिखने का तरीका है ये. So this sigma is nothing but activation function here, activation function, and this is again the weighted sum. This one is the bias. Okay, this is the weighted sum w1 x1 plus w2 x2, and we apply some activation function blah 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 to get output. We'll be looking at it, don't worry. ये बस एक तरीका है उसे लिखने का, the same thing. And this is the predicted output, which we call as activation in other terms also. और इसमें like when you go into detail, you always denote these notations in vector forms or as tensors. डोंट वरी, अभी तुम्हें इतना डेप्थ में जाने की जरूरत है नहीं टेंसर्स वगैरह में, बट यू शुड बी नोइंग कि व्हाट्स द स्टैंडर्ड कन्वेंशन टू डू दैट. ओके, सो ये जो एक्टिवेशन फंक्शन है, आई वाज सेइंग, दीज आर द टाइप्स फॉर देम. फॉर एग्जांपल सिग्मॉइड मैंने बताया था, 1/1 + e⁻⁻x. इसका ग्राफ तुम लोग देख सकते हो, ग्रीन वाला. 0 to 1 के बीच में सारे आउटपुट अपने आते हैं. ओके, माइनस इन्फिनिटी पे this value would be tending to 0, and plus infinity पे this value would be tending to 1. Another example is tan hyperbolic x, that is nothing but uh, e to the power x minus e to the power minus x upon the sum of the two. उसका ब्लू वाला ग्राफ है -1 to 1 है, सॉरी, -1 to 1 आते हैं उसका आउटपुट्स. And ReLU function, the most you will be using, at least I would say, जब तक तुम सीख रहे हो, जब तक तुम ऐसा खुद को प्रो नहीं मान लेते कि मुझे आता है, तब तक तुम मोस्टली रेलू ही अप्लाई करोगे. कुछ नहीं, नेगेटिव वालों को 0 कर देता है, पॉजिटिव वालों को सेम रखता है, इतना ही है. ओके, maximum of 0 comma x. So obviously, for x greater than 0, your graph would be y equal to x, and before that it would be 0. Okay, तो ये बहुत सारे एक्टिवेशन फंक्शंस हैं, तुम लोग बाद में देख सकते हो. डेक आई विल बी शेयरिंग विद दिस यू, सो नो इश्यूज विद दैट, जस्ट फन वे टू लुक एट इट. एंड द लॉस फंक्शंस, जो हमने बोला था कि आर मॉडल विल बी ट्रेनिंग ऑन द लॉसेस अकर्ड इन इट्स ईच रन. ओके, so there are different types of losses also. First is the, जो मैंने बोला था कि मॉड्यूलस लगा करके लॉस ले लोगे. वैसे लॉस किसका आ रहा है इसमें, मैं पूछना भूल गया, लॉस किसका निकाल रहे हैं, किस चीज में लॉस है ये?
भैया जो एक्चुअल वैल्यू से डेविएशन है।
हाँ, बस वही वाला, ठीक है. मैं मेंशन करना भूल गया था. तो ठीक है, जो तुम बेसिकली मॉडल की एक्यूरेसी तुम उसी पे देखोगे कि प्रेडिक्टेड वैल्यू कितना है, एक्चुअल वैल्यू कितना है. सपोज आई हैव 4 points belonging to the line y equal to x, और मैं मॉडल ऐसा ट्रेन करता हूँ कि एवरी फिफ्थ रिजल्ट इट गिव्स मी अ रॉन्ग वैल्यू. तो वहां पर जो मेरा डेविएशन आएगा उस वैल्यू में फ्रॉम द एक्सपेक्टेड वैल्यू, वो मेरा लॉस होगा. ओके, सो दिस इज मीन एब्सोल्यूट एरर, MAE. दिस इज मीन स्क्वायर्ड एरर, MSE. नथिंग बट कि मॉड्यूलस को हटा करके तुम स्क्वायर कर दे रहे हो. एनी आइडिया कि मतलब मॉड्यूलस में भी काम चल ही जाता है, तो स्क्वायर करने की जरूरत क्यों पड़ती है? लाइक अलग बनाना, बनाया ही क्यों? बस तो मैग्नीट्यूड बढ़ जाएगा थोड़ा सा. एनी आइडिया?
भाई आउटलायर वैल्यूज को कम वो करने के लिए।
हाँ, सही है, सही है. बेसिकली वही है कि आउटलायर वैल्यूज जो है तुम्हारे, उनमें मतलब ये भी पार्ट ऑफ अ रीजन है, नॉट एग्जैक्टली द रीजन. वन ऑफ द मोर अप्रोप्रिएट रीजन ये है कि उसका तुम आगे जो ऑप्टिमाइजर्स यूज करते हो टू ऑप्टिमाइज द लॉस फंक्शन, उसमें कंटिन्यूटी ऑफ अ फंक्शन प्लेज अ मेजर रोल. ओके, और तुम अगर मॉड्यूलस वाला फंक्शन देखोगे, ऐसे आएगा सपोज एट सम पॉइंट, और इसके आगे यहाँ पे ना, ये वाला पॉइंट नॉन नॉट डिफरेंशिएबल होता है, और क्या होगा जेई में भी, है ना. और अगर मैं इसी चीज को स्क्वायर में लिख देता, ऐसा कुछ चले जाता MSE के लिए. तो मेन रीजन यही है MSE का, कि आगे तुम जो ऑप्टिमाइजर यूज करोगे टू ऑप्टिमाइज लॉस फंक्शन, कि तुम्हें लॉस कम करना है, तो उसमें कुछ ऐसे एल्गोरिदम्स है जिसमें कंटिन्यूटी एंड डिफरेंशिएबिलिटी ऑफ अ फंक्शन प्ले अ मेजर पार्ट. तो उसके लिए हमें स्क्वायर वाला चाहिए होता है. एंड BC is binary cross entropy. We would not be going into detail for this at the current moment, but you can go through it. Resources में हमने डाला है उसके लिए, है ना. तो और हाँ, ऑल्सो ओपन सीवी वाला जो पार्ट था, एजेस एंड कंट्रोल्स, उसके भी रिसोर्सेस अच्छे से गो थ्रू कर लेना। कोड स्निपेट्स दे रखे हैं, उससे भी चला करके देख लेना। गूगल कोलैब में ही प्रेफर करो रन करना, क्योंकि लोकली तुम एक सेटअप बन जाता है तुम्हारा। यू वुड हैव टू जस्ट लोड द इमेज एट दैट पर्टिकुलर कोलैब लोकेशन, और फिर तुम उस इमेज को फिर एज अ सोर्स बना करके आगे कहीं भी यूज कर सकते हो। क्योंकि पाइथन इंटरप्रेटर्स में जाओगे तो मेन इशू वही है कि जो स्टोरेज वाला पाथ जो तुम्हें डिफाइन करना होता है ना लैपटॉप में, तो बहुत बार कुछ फोल्डर एक्सेस में दिक्कत आ जाती है या फिर कुछ और दिक्कत हो जाती है। तो टू बिगिन विथ वी वुड बी सजेस्टिंग यू गो विथ कोलैब इटसेल्फ। तो ओके, बीसीई बस एक देख लो कि फॉर्मूला होता है पी ऑफ वाई आई इज नथिंग बट प्रोबेबिलिटी है। थोड़ा सा प्रोबेबिलिटी में चलता है यहाँ पे काम, है ना। तो लॉस फंक्शन की डिपेंड्स ऑन द टास्क, मन से तो नहीं उठा सकते ऑब्वियसली। तो मीन स्क्वायर्ड एरर इज यूज्ड फॉर द रिग्रेशन टास्क, एंड बीसी क्रॉस एंट्रोपी इज यूज्ड फॉर क्लासिफिकेशन टास्क। तो ये मैंने जो बोला था कि द लॉस फंक्शन मस्ट बी डिफरेंशिएबल, क्योंकि तुम्हारे मोस्ट ऑफ द ऑप्टिमाइजिंग एल्गोरिदम्स जो होते हैं उनमें डिफरेंशिएबिलिटी प्लेज अ मेजर रोल व्हेन यू अप्लाई देम फर्दर। तो अभी तक तो बेसिक्स था। क्लियर विद दिस ऑल ऑफ यू, लाइक गेटिंग जस्ट नोइंग द टर्म्स। अभी तक तो कुछ किया नहीं है।
हाँ भैया।
कोई इशू किसी को?
भैया आई हैड अ डाउट, आपने बायस की यूज किया था?
लाइक बायस जो तुम्हारा है ना, ऐसे समझ लो कि अब मैं सपोज इफ आई वांट टू प्रेडिक्ट वेदर प्रेडिक्ट द कॉस्ट ऑफ अ हाउस एट सम लोकेलिटी एट सम टाइम इंटरवल, मतलब एट दैट पॉइंट ऑफ टाइम। तो उसमें एक फैक्टर आएगा तुम्हारा कि लोकेलिटी कैसी है, एक फैक्टर आएगा तुम्हारा कि उसका फर्निशिंग कैसा है, एक फैक्टर आएगा कि हाउस का टोटल एरिया कितना है, एक फैक्टर आएगा कि इसके प्रीवियस ओनर्स कैसे थे। मतलब ये बहुत छोटा सा फैक्टर है, लेकिन दिस कैन अफेक्ट टू। तो जो बेसिकली अब ये सीन हो सकता है कि रिसेंटली अगर उस लोकेलिटी में कोई चोरी हो गई, है ना, तो जब वो चोरी हो जाती है तो उसमें एक फैक्टर तुम अब एक्स्ट्रा ऐड तो कर दोगे कि लोकेलिटी में थोड़े से पॉइंट्स घट गए सपोज। लेकिन वो पॉइंट्स तो तुम्हारे तुम खुद से जब ऐड करोगे तभी घटेंगे ना। तो यू ऐड अ बायस टू टेक केयर ऑफ ऑल पॉसिबल वेरिएशंस, की मतलब नॉट एवरी फैक्टर कैन बी इनकलकेटेड व्हाइल यू आर ट्रेनिंग योर मॉडल। तो बायस कैन, तुम ऐसा समझ लो कि टू बेसिकली कीप अ चेक कि थोड़ा सा वेरिएशन वाला फैक्टर भी हो जाए, और वो वाला सीन है। ओके,
ओके भैया।
लाइक थ्रेशोल्ड ही मान लो। मतलब इट वुड बी इजी फॉर यू व्हाइल यू विल बी लर्निंग द कंप्यूटिंग पार्ट, कि काइंड ऑफ थ्रेशोल्ड होता है कि यू वुड बी गोइंग अबव दैट बिलो दैट, लेकिन टेक्निकली थोड़ा सा अलग होता है वो। ओके,
ओके भैया।
तो ओके, एक परसेप्ट्रॉन एग्जांपल देख ही लेते हैं। So let's say a student studied for 5 hours, that is x1 is 5, and he had 90% attendance, x2 is 0.9, assuming weights w1 is 0.6, कि मतलब for the number of hours studied the weight is 0.6, and w2 is 0.4, that is the percentage attendance उसका weight कितना है, वो है 0.4, and bias b is -0.5। कि अब यहाँ पे तुम -0.5 इसीलिए कर सकते हो क्योंकि 5 घंटे, अब उसकी अटेंडेंस भले ही 90% थी, लेकिन इट डजेंट ऑलवेज मीन कि वो क्लास में पढ़ ही रहा था। तुम लोगों ने फर्स्ट सेमेस्टर में थोड़ा एक्सपीरियंस भी कर ही लिया होगा कि यू डू नॉट गो टू ईच क्लास टू जस्ट स्टडी, इजंट इट? हेलो हेलो।
हाँ भैया।
तो वही बायस थोड़ा सा तुम इंट्रोड्यूस कर दे रहे हो कि फॉर अ गिवन अटेंडेंस एंड आर स्टडीड रेशियो, इट डजंट ऑलवेज मीन कि वो फुल कैपेसिटी पे काम कर रहा था वहां पे। देर आर चांसेस कि ही माइट हैव बीन इनएफिशिएंट एट सम टाइम। तो कैलकुलेट द वेटेड सम। कोड तो वही है कि वेटेड सम इज W1 x1 प्लस W2 x2। उसको तुमने ये पुट कर दिया, वैल्यूज पुट कर दी, और फिर वो आ गया तुम्हारा 3.36। अब उसमें बायस ऐड कर दिया, बायस ऐड कर दिया तो वैल्यू हो गई तुम्हारी 2.86। और उसमें एक एक्टिवेशन फंक्शन सपोज तुम ऐड कर देते हो कि सपोज एक्टिवेशन फंक्शन तुम, अगर मैं 1.5 भी बोलूँ यहाँ पे, एक काइंड ऑफ, इफ आई से कि मेरा जो टोटल आउटपुट आता है इफ इट्स ग्रेटर देन 1.5, विल डेफिनेटली पास इन द एग्जाम। ऐसा बोल सकता हूँ। वैसे तो मतलब काफी सारी चीजें हैं, 1.5, 1.2, 0.2, 0, 1। तो डिपेंड्स ऑन द एक्टिवेशन फंक्शन आई हैव यूज्ड। तो अलग अलग, ये तो बस एक सूडो कोड है कि बता दे रहे कि ऐसा होता है ना। यू कैन रीड इट हियर एज वेल। If the weighted sum plus bias is greater than or equal to 0, output 1, that is pass, otherwise output 0, fail. You can change this condition for equal to 0 or that one. Obviously तुम change कर सकते हो according to your needs. Okay, so that was a quick example for the same. तो अभी तक तो ये सारी बातें हो रही थी कि how does one perceptron work, like you provide inputs with weighted with the weights attached to it, like how much it would affect the output for that particular function. You apply some activation function and then ponder upon the error key, what should I do further to make my function a better one, make my model a better one. So that's what a perceptron model is. So multi-layer perceptron is nothing but when we add many such layers. So you can see the input x1 is attached to these all neurons with some weights W11, W12, W13, a different bias for this hidden layer, different bias for this hidden layer. Okay, and this x2, this x3, this x4 similarly connected. These hidden layers are fully connected in between them, meaning that there is not it is not necessary that all the inputs would be corresponding to all the neurons in the first layer itself, but the intermediate hidden layers, which I'm calling, they are all fully connected. So this is just to fine tune, like when you have अब मतलब अगर तुम सपोज एक ही वेट अटैच कर रहे हो, you are basically accounting for W1 x1, but there is a possibility that x1 might be going with W1 squared x1 for the same output that would be fitting the model better. So for that we just add another layer and we would be optimizing the other weights as well to fit our expected model. Okay, so that's why we need to add the hidden layers. Hidden layers is nothing but middle multiple layers for the same model. So this is nothing but the neuron one, output for the neuron one, nothing but weighted sum. उसी को वेक्टर फॉर्म में लिख दिया है थोड़ा सा. ओके, सो दीज आर ऑल नोटेशंस. नो नीड टू वरी अबाउट दिस एट प्रेजेंट. बहुत ज्यादा डिटेल में जाने की जरूरत नहीं है, बट यू शुड बी नोइंग ऑल अबाउट दिस. वैसे पूछ ही लेता हूँ, व्हाट्स द डायमेंशन फॉर दिस मैट्रिक्स? विच ऑर्डर मैट्रिक्स?
वन क्रॉस एन।
N×1।
आ गए दो अलग आंसर. बताओ अब, 1 क्रॉस एन है या N×1 है?
वन क्रॉस एन।
1 × n।
भैया
रो
वन
रो
क्रॉस एन
कॉलम।
प्लस वन
1 क्रॉस।
1 × n+1, yes, that's the right answer because there is W0 से शुरू हो रहा है ये. बट 1 × n भी मतलब ठीक है, आई विल गिव दैट. N×1 वहां पे दिक्कत आ गई बिकॉज यू नीड टू डिफाइन रोज बाय कॉलम्स. you've done the डिफरेंट थिंग फॉर इट. तो ध्यान रखना आगे, मतलब मैथमेटिकल चीजों में थोड़ा सा दिक्कत हो जाती है फिर आगे. और द सेम. ओके, इसका ऑर्डर बता दो. इस स्क्वायर मैट्रिक्स का स्क्वायर है क्या? स्क्वायर तो नहीं है, क्या है? ऑर्डर बता दो इसका.
K cross N.
K comma
ओके
N.
ओके.
K cross N.
नाइस नाइस नाइस. So okay, you all are attending actively. Good to hear that. Okay, so like now we are up to the stage that we have calculated the weighted sum. Now what next? So weighted sum के बाद वो our step was the activation function, and after the activation function we need to ponder upon the error कि error यार ज़्यादा आ गया कम आ गया, and how do I train my model to go further. Okay, what changes should it make to its parameter? Now obviously when you will be training a model, you will be initiating all these vectors, you will be initiating these vectors for some random 0 1 0 1 0 1. Okay, because you'll never know what is the exact fit for it. But you train your model to update the weights and the bias in each run. So that's what makes it a learning model, a machine learning model. Okay. So here we'll be looking onto our gradient descent algorithm for to optimize our code. So when we look at the pseudocode, not exactly pseudocode, we just increment the weight for that particular neuron with wt minus eta times of del of wt. Okay, del is nothing but partial derivative, because partial यहाँ पे use किया because there can be many parameters. So obviously you will have to differentiate with the corresponding variable and not with all the variables. Okay. So to keep it simple, we will be just playing with w comma b here, because the loss function L is just a function of w comma b. Okay. So in reality, इसमें w में it's w0, w1, w2, w3, etc. So it becomes a 3D model. I'll just give you a glimpse about the 3D model as well further. So creating an algorithm to optimize our code. So we'll be initiating t to 0, and suppose maximum iterations is 1000. So while t is less than maximum iterations, just we have to update wt plus 1 to wt plus 1 as wt minus eta into uh, del of wt. Okay. And we'll be incrementing t as t plus 1 in the end to keep in count the iteration. Okay. So any doubt up to here? All good? Okay, I'll take that as a yes. I'll proceed further. There are a couple of hands raised. Any doubts? Just previous one. मैंने बोला था हाथ ऊपर करने के लिए. I guess I'll just continue further. My screen is visible, guys.
Yes, भैया.
Okay, thank you. Okay, we'll just move to the presentation part again. So up to this algorithm, we just have to update. Now, also, eta is some constant value, not a variable here. For the normal gradient descent method, eta is a small constant value, because you obviously don't, there are chances. I'll just depict in the graph. See, you can see here. Uh, I'll annotate a bit. This point, it has a very high del, what was that, del omega t value. Okay, so you can't just you can't directly do wt minus del of omega t, because that's a very high value at this point. It's almost tending to, I would say, infinity. So for that purpose, we just multiply a small, very small value eta, so that also our steps are maintained, like we don't increment too much at a time, because we don't want to miss the optimum point before and then move on towards infinity again. That's the main purpose. Okay. So I have chosen the activation function as the sigmoid function. So my output y equal to fx will be 1 upon 1 plus e to the power minus of the omega x plus b. Okay. This is nothing but weighted sum plus bias, which we have calculated in the previous page itself. This is our output, and we'll be calculating the error by fx minus y whole squared. Okay. MSE. So let's assume there is only one point to fit x comma y. This is all the derivation. This is for your further references when you open the deck. Loss function is a function of omega comma b. Um, Half is just for the just to make things out even. Mm, you don't need to mind about that half. You can omit it also. So when you calculate del omega, that is partial derivative of loss function with respect to omega here. So you just further differentiate it with the partial function, sorry, partial derivative. So accordingly, this is all maths. Just have a quick glance at it. Uh, I don't think I need to explain too much about this because everything's pretty well explained in steps. So just you need to see what matters, that del omega is this value, fx minus y into fx into 1 minus fx into x. Okay, like they have come up to this stage, and this stage has been carried on here. Okay, so this is all maths. I think you all will be able to do that. So what's our final value? Fx minus y, the error, into fx, the predicted value, into 1 minus fx into x. What was x is nothing but input. So this model is for a single input, single output model. For 2 points, you can apply the same, just we need to replace x with xi everywhere because there are two inputs. Okay. So del omega will be changed accordingly, and it would nothing but be a summation, and you'll just replace it in the code here. Like you have calculated the del omega, multiply with eta here, and you'll be updating your wt plus 1 uh, with each iteration. Okay. So anybody needs that I should explain this derivation, or shall we proceed? It's just mathematics. I think you'll be able to understand it just by having a good look at it. So shall we move forward?
Yes, भैया.
Okay, okay. Thank you. So why does this work? Okay. Like you have just implemented gradient descent, not exact code, but you obviously know the algorithm. So if you know the algorithm, you can always get the code for it. So why does this work? So here's a depiction for the same. R theta is nothing but loss function. Okay, I'll just a minute. R theta is nothing but loss function, and theta here corresponds to W comma B. Okay, theta is a generalized form to represent the parameters. So theta I would be representing W comma B, like theta 0 will be W, theta 1 will be B. So accordingly, you will calculate the partial derivative del theta I into loss function. Okay. So if you're at this point initially, you've chosen W is equal to W1. Okay. You've chosen this. and it's this point currently. So you can see the derivative here is negative, okay, and you've already put a negative sign in your formula already. So in the so the formula updated one will be W2 is W1 minus something into the derivative of this, and derivative is already negative. So overall you'll be incrementing something to W1. Okay. So you'll get your W2 somewhere here as depicted here. Okay. I'll again say the derivative here is negative and there's already a negative sign in the formula. So minus minus becomes plus and you'll be incrementing some quantity, some positive quantity to the originally selected W1. And further, here the same thing, like the rate of change, the derivative is negative. There is already a negative. So overall, you will be incrementing something. Now, after incrementing, you've crossed the local minima and you've reached some point ahead. This is very much possible in this approach. So no need to worry about that. Now here, the derivative becomes positive. You can see the slope is positive. So the derivative is positive and there is a minus sign placed with the derivative. So overall, you will be decreasing some value into the previous W. Okay. So you would be going back. So after many such iterations, it doesn't always converge in 4 or 5 iterations. It takes many of them. So after many such iterations, like 1 year, 1 year, 1 year, 1 year, it might also go year, like year, and then finally it would converge to local minima. Mostly to local minima, it might happen that a bit of deviation might be there, but it doesn't affect too much because we are almost close to the local minima, so our optimizer function has worked. So this is how this works. And as I said that when we go on increasing the parameters, it becomes a 3D model to play with. And you can see the local minimas and maximas in this particular picture. So it would be going along when you would be differentiating with respect to some particular parameter, that is suppose mm, theta I is equal to some wj. If it be differentiating with respect to this, there would be a plane marked out like this. So you would be playing on this plane. Okay. So that's how it works. So when you calculate the overall loss function, it would be a compilation of all the local and global maximas, minimas over a 3D plane. Okay. So any doubt in the working of the algorithm? Anything you want to ask? Anything you want to have a look at again? I'll switch to the slide if you want. Okay. So shall we proceed further? Like we are done with the neural networks almost. Optimizers, as I had said, uh, stochastic or mini batch GD, that is nothing but stochastic gradient descent. That's one of the advanced optimizers. We'll not be looking at it currently, but you will be looking at it. You can look at it. I think they are uploaded in the resources. I'm not sure with the SGD part, but I think we have uploaded the stochastic gradient descent also. You can have a quick look at it. You'll have to watch a few lectures regarding to it. So I'll just brief you what's a stochastic gradient descent. So basically, I had said that eta is a constant in this formula. Eta is a constant in our gradient descent. In stochastic gradient descent, like we change the eta also with respect to how fast our del is changing. Okay. So if I'm not wrong, we go with del square omega t in the SGD part 2. So we increment our eta as well as per the needs, so that we don't, like in this case you had seen that we had jumped across the local minima and then again made our way back to the local minima. So in SGD part, you'll be having a point here, then here, then here, then here. You'll be having smaller steps, and finally you'll be crossing the local minima, like stopping at the local minima. That's the stochastic gradient descent part. Uh, Also, one of the most advanced, modern, widely used optimizer is adaptive momentum estimation. That is ADAM. There's a resource for it. I've seen it, so you can go through it in the resources section. Okay. Okay, overfitting and underfitting, the same thing. Like have, if you don't train it properly, there are chances it won't catch the pattern properly. You need a balanced graph. But if you keep the number of epochs, that is nothing but number of iterations too low, it won't fit the curve perfectly. But if you keep too much, so it might also deviate according to the noise of the points available in the graph. So that's the case. Okay, we are done with the introduction to neural networks. So up till now, up to the neural networks part, any doubts, any issues? I know this might feel a bit boring, but like you cannot have all the fun things all the time. You need to have some mathematics as well to make it a bit more funny. Okay, so any doubts? Yes, no?
Bhaiya, I had a
Hello?
doubt. Those formulas
Yeah, yeah,
that
yeah.
you showed for those, is it like predefined that we need to apply these formulas only for the
For the
low
loss
stuff and
functions,
all? Yes.
just a minute. I'll switch to the slide of loss functions. These one,
No, for the gradient part you show.
gradient part. Okay, this one, this iteration part. Okay,
Yes.
like I have just demonstrated a simple basic algorithm called the gradient descent. Like you go along the gradient. There are obviously many other algorithms where they take in consideration of other parameters as well. So when you go to a newer optimizer, that is a newer algorithm, you will be having a different formula. But if you go to the gradient descent part, the basic part is this one. But if you want to optimize it as well, so the stochastic gradient descent, like I had said, like you change the value of eta also in the SGD part. Okay. So formulas are, yes, you can't change too much. Okay, you can change the parameters. Like you can change the value of eta for your particular model. Like you can place it 0.002 or 0. Like 10 to power minus 4, 10 power minus 6. You can start with it. No issues with that. That's all you can experiment. But the formulas, I guess, different formulas for different algorithms. But for algorithm, the formula is almost the same as defined. Okay.
Okay, Bhaiya.
Okay. So we'll proceed to the CNN part now. It would be a bit more like in robotics, you don't really need neural networks in depth, but you really need CNN in depth. So CNN is nothing but convolutional neural networks. That is a subpart of the neural network section. So now, like you had seen in the previous session, OpenCV session, there are images with many pixels. Okay. So like if you have a 32 cross 32 image also, it's I think 1024 pixels in total. Now for each pixel, if I represent a matrix consisting of the RGB values for that pixel, so you have 1024 into 3. that's the total number of pixels, like that's the total number of parameters you'll be dealing with. And now that goes on increasing if you like increase the pixel size, image size and all. Like if you have thousands of pixels, so what can you do? So one major drawback in the normal neural networks was if it cannot directly handle too many parameters. So to handle that issue, we switch to some other modified methods. So one of them is convolutional neural network, mostly used for image processing, feature extraction. You can see here. Just a minute. So there are different steps. Convolution plus ReLU. The ReLU is nothing but activation. Okay, everywhere ReLU is activation function. Convolution, I'll be explaining it to you in the coming part. So pooling, padding, flattening, flattening the dense layers, fully connected layers, softener prediction. All these will be having a quick glance at in this introduction, and then you'll be um, applying this in your models using TensorFlow. Okay, in the resources we have provided you, we have introduced you the library TensorFlow. But if you want, you can obviously go for PyTorch or Keras. You can use all that. But for now, we are stuck to TensorFlow itself. Okay. Okay. Moving on. The definition. Uh, Learn kernels, that is tensors. Tensors is nothing but multidimensional arrays. Like I had said you, 32 cross 32 image. These are the number of pixels, and each pixel has RGB values. So this has become a 3D matrix. Okay. So these are the tensors. Uh, you don't need to go in real depth for the mathematics part, but just you need to have an idea how does that work. Okay. So and also CNN is nothing but feature extraction part, like you can see in this image. If you I want to look for a particular feature, that is I have to look for a number 2 encoded in, suppose here we have depicted in the black and white format, binary or grayscale. But when it comes to the colors, there are too many operations to go with. So if you want to extract a particular feature, that is the I would say I want to look for the number 2 in a particular image, I'll be moving a filter, I would say, like it would be encoded with all the features that a ideal number 2 must have. So now it is not necessary that, like if I tell all of you to write the number 2 and give it to me, there will obviously be deviation in all the depictions. But our model is trained accordingly to uh, I would say, be assisted with all those errors and to predict that yes, this is the number 2 in this particular image. So we just move across a filter, that is kernel. Okay, that is nothing but the convolutional layer. So for a particular feature extraction, we move that. So that's the basic idea, to look for a particular feature in a image. So why? Okay, the same thing like the drawbacks, weight sharing and local connectivity, connect convolution. I'll explain that further. Use multiple filters, convolve over inputs, and reduce the number of parameters. That is, demonstrated that you can't like always deal with 3072 parameters, because these would be again corrected to, if I say 10 layers of neurons. Okay, and each layer has 10 neurons. So that is 3 lakh, almost 3 lakhs parameters to deal with for a model. And the more you increase this value, and this value, the more you want to extract the features, the more you want to train your model properly. So the features will be just increasing. So to just compress those features, we use the convolution part. Okay, that's the main reason. Uh, So we also have a feature detector, also known as a kernel or a filter, which will move across the receptive fields of the image, like I had demonstrated. I want to find the image 2 in a particular image. So it would be moving a particular filter or kernel that would be encoded with all the information required to capture the image 2. Okay, that's the main mode. So this checking if the feature is present. This process is known as the convolution. Okay, filters. Okay, this is all theoretical part. So basically, coming to the implementation. If these are all values for suppose I would say for a grayscale image 0 to 255. These are all the input values for each pixel, and I have applied this particular filter 0, 2, 1, 4, 1, 0, 1, 0, 1, 1. This one. Okay. So how does the filter work? So for these 9 pixels combined with this filter, there would be one single output. Okay. So here there are two things coming in action. Like you can see the mathematical process, what's exactly happening in it. And so basically you are, this filter would be for some particular feature. Not exactly now. For two, it would be a different case. Like I have to find the number two or find the number six or some, I have to find a zebra, find a giraffe, something. So all the filters for the corresponding pixels would be different. But just for example case, I have applied this filter. So you can see that this 5 cross 5 matrix is now compressed into 3 cross 3 matrix. And according to the filter, we get the output. Okay. So the first element here is 16, like 9 into 0 plus 4 into 4 into 2. So all this corresponding multiplication. And so we have done two things, that is to compress the input image, like to, we also don't want to lose our data, like it's not possible कि तुम सीधा image को काट ही दो कि you just crop it and just put it into the model to train. So you need to also